All right, guys, welcome. So today we're going to talk about some basic numerical methods for solving first order ODEs. So this will basically talk about how we can use um, software that's built into computers in order to solve ODEs that either may be too hard to solve by hand or actually impossible to solve by hand. All right. So the first thing that we need to start off with is that typically we'll see in this sort of this development here, the first thing we're going to talk about is what's called Euler's method. And we're basically going to define, I guess I can't get any closer there. We're going to define our derivative as some function. So our y prime is going to be some function of x and y. So that will be one thing that potentially will come up here sort of in the derivation of these methods. But so that's just one thing to sort of keep in mind here. Another sort of preliminary thing that we should mention here is that a lot of these numerical methods for solving these ODEs are done on some, and I put them in a quotation, some finite domain size, because we of course know that the open set A to B is an uncountable infinite set. But what I mean by a finite domain size is that this doesn't go off to either positive or negative infinity, right? So we assume that this is some sort of closed finite length interval. Right. So now the first thing that we're going to consider is we're going to partition our open interval from A to B into a collection of x values. So similarly to when you talk about sort of the development of integration, right? The first thing you sort of do before you talk about the definite integral is you think about breaking your interval that you're integrating over into a partition, and then you basically pick some rectangles and then you increase the number of rectangles, right? So we're sort of doing a similar thing in that sense, where we want to partition our interval into sort of a bunch of different x values here. Right. Now, one thing that you'll notice about each of these x values here is that they're all separated by a value of h. And that h is what we refer to as the step size, right? And of course, if you want something accurate, if you want an accurate estimate, you usually take your h values to be small, right? So they're sort of like, like obviously like an h size of 5 would probably not be too enlightening. So like common values might be like 0.1 or 0.01 or something like that, right? And then depending on how much you want to balance using energy to compute things, of course, the smaller you make your step size, the more calculations you're going to have to make. So there's sort of a balancing act there. Okay, so now if we consider the idea of Taylor expanding, or a Taylor series, I should say, for y of x plus h, we sort of get this thing popping up where we have powers of h. Now, if h is chosen to be small, those higher powers of h, right? So if h is small, h squared is even smaller, and then h to the third is even smaller, and so on and so forth, right? So if you wanted to, you could ignore your higher powers of h. So ignore higher h powers. And you get sort of this, this very basic estimate where it's sort of a first order. It's the local linear approximation, right? You're only expanding out to the linear term and taking that, right? So this sort of motivates the idea for what's called the Euler method. Now, in practice, and I'll mention this a little bit later, well, I actually mention it right now, but now you compute your next, so the basis of the Euler method is you compute your next y value, right, your next n+1 y value with the current y value, and then plus, remember we said that the f of xy was sort of like your y prime. So we multiply that by h and then, by the derivative at that previous point, right? So essentially you are, again, using the local linear approximation to figure out what the next point is. right? So now this is what's called a first order method, right? And hopefully that's for obvious reasons because you have your h to the first power there. Now the approximation is not very good. I use the word crude here, so you get sort of like this coarse approximation, and you get subject to a lot of round off errors, right? So in practice, the Euler method is not a good method to use to numerically solve any ODE, but for the sake of pedagogical purposes, the Euler method is good for sort of introducing us to some more useful numerical methods, right? Now, one thing that I'll sort of mention here in passing, and that's that in all of these sort of things that we're going to consider, we have that our h is sort of fixed, right? So if we pick h to be 0.2 or whatever, then that's what it is the entire time. Now, one thing that modern software does is they use something called adaptive step sizes, right? And essentially what happens is that they're going to change, the computer will sort of, in a clever way, change h as needed, in order for your approximation to be accurate to some specified level, right? So if you don't want the error to exceed some certain value, you tell the computer that, and it will change the step size as needed in order to not exceed that error, right? So that's one thing that we'll sort of mention in passing here. But as we go through, obviously we're not going to do adaptive time stepping by hand, but that is one thing that is typically done behind the scenes when you're doing this in a computer. All right. But anyway, so now that we've talked about the Euler method, we can now talk about what's called a little bit better version, the improved Euler method. All right. Now for the improved Euler method, the idea is that we want to consider more of these extra terms here, right? So we want to consider sort of the next couple terms there, all right? But there's sort of a fundamental problem with this, right? So we know, that, of course, that y depends on x, and now f, right? F is your f of x, y, so it's depending on x and also depending on y, which is also dependent on x, right? So f is going to take a little bit of work to find, and of course, that then means that f prime, f double prime, f triple prime, and so forth are going to be, it's going to take quite a bit of effort to find them, right? So we're not going to find them specifically. What we're going to do instead is we're going to avoid that problem by basically computing some certain values of f that's going to allow us to sort of avoid finding explicit forms for these derivatives. And we're going to do so in a way that gives us the highest accuracy, right? So that's, of course, something that's good, because the more accurate your answer is, the more sort of meaning you can take from it, right? So in the improved Euler method, at each step size, we have to do two things. Oh, sorry, at each step, not each step size. At each step, we have to do two things. We have to find what's called a predictor, which is essentially, this is just done using the first Euler method, right? So you find your next y value by using the one that you currently have, and then you add sort of the local linear approximation to it, right? Now you notice here that instead of yn plus 1, it's y star n plus 1. All right, and that's because this is an auxiliary value. Now, once we have that predictor value, we then find what's called the corrector, right? And then once you have the corrector, you can find that by, now sort of what you're doing is you're sort of taking an average. So you see, you sort of have this 1/2, and then this average here of the one that you would normally use, right? So the f of xn, yn, and then also you're going to use, this term is coming from that auxiliary value, that predictor that we just found in the previous step. And that's going to refine your accuracy a little bit. But let's sort of take, let's take a look at a particular example, and we'll sort of see how we can sort of apply this to a particular example. Okay, so we're going to assume that our problem is y prime is equal to 2 times 1 plus y squared. And of course, we're just taking the initial condition of y of 0 is 0, which basically means that our first point is 0, 0. right? So this is like x0, y0. All right, and we're going to take our our step size to be 0.2, and we're going to do improved Euler. All right, so at each step, we need to find a couple of things here, right? So we need our h times f of xn, comma yn, which I'm going to call k1, right? And that's found by taking 0.2 and then summing xn plus yn, right? And then, right, so this is just h, and this is my f of xn, yn. Okay, and then when we find our new f of xn, sort of with this auxiliary value, that's what's coming in to this thing, right? So now when we plug that in and we find our next, our y at n plus 1 point, and we plug all this stuff into the formula, we're going to find that yn plus 1 is yn plus 0.22 times the sum of xn plus yn plus 0.02. Right, now, rather than bore you with the calculations, you can verify that you're going to find these values in this table here. Right, so of course there's your 0, 0, your first point, and then at each step here, you're increasing your xn by 0.2 each time, and then your y values will sort of follow suit as to what falls out in the formula. Right, so that's sort of the idea behind the improved Euler. So the improved Euler, of course, is a little bit better. It's a second order method, so it's a little bit better. But for the most part, improved Euler is still not something that's really used a lot in practice, right? Now, generally, the most important one, or one that seems to be the most important, is the Runge-Kutta method of fourth order, which is usually just called RK4. All right, if you're going to call for it in a programming language, usually it's referred to as RK4. Now, the idea of RK4 is basically you're computing these 4 auxiliary values shown here, and then you're sort of taking your yn plus 1, and then you're sort of finding like a weighted average here that's dependent on those auxiliary values, right? So again, if you want to see an example, so sort of with the same example that we just did, but how does Runge-Kutta handle this better? So here we have our 4 auxiliary values, right? So that's what we need for each step. And then, of course, the calculations you can find would be given by this table here, right? And now you're seeing that in this error column, you're getting some quite value, or you're getting some quite small values, right? So they're on the order of 10 to the minus 6, which is, of course, good. And now if we compare the 3 methods, you can see that that RK4 does significantly better than Euler and improved Euler, right? So for the most part, that's what's used as far as numerical computing goes. I know that for my research in particular, the program that I use uses RK4 as well. Now, one thing that is also of interest that I'm not going to go into any detail about, but you can sort of find on your own if you're interested, is the idea of backward Euler. Now, the backward Euler method is similar to the Euler method, of course, but is used for what are called stiff ODEs. And essentially the idea for backward Euler is that you're using, so you're almost finding future values in order to find what the past values are, right? So that's one thing that's interesting that I'm not going to go into too much detail about, but that is another sort of method that's out there. But I wanted to just sort of touch on mainly improved Euler and RK for it. All right, so that wraps this video up. I hope you enjoyed this little intro to numerical methods for solving ODEs, and I will see you next time.